What note was that long pitch? If you said it was a B flat, you're mostly correct. The musician sees chords and instruments that sound good together to evoke feelings. The mathematician sees an amalgamation of sound waves vibrating the hair cells in your inner ear at different frequencies measured in cycles per second. Waves with high frequency sound
faster and higher pitch,
whereas low frequency sounds
lower and lower pitch.
When two waves add, the resulting period is the least common multiple of the two original periods. Waves with smaller periods and regular patterns sound like constant tones, whereas longer and more complex patterns sound dissonant. Octaves, which sound like the same pitch, are separated by a factor of 2. Now there are 12 half steps in an octave, so the common ratio between each note must be 2 to the 1/12. The human ear cannot discern differences within 1% of the actual note, therefore it's appropriate to approximate the powers of 2 to the 1/12 as fractions. 12 is an arbitrary number, but it was chosen for a reason. It works out such that most of the powers of 2 to the 1/12 approximate to simple fractions. If these numbers correspond to a C scale, we'll see that E to C has a ratio of 5/4, and that G to C, a perfect fifth, has a ratio of 3/2. Because they're both simple numbers, they create pleasant sounds. Now on the other hand, F sharp to C creates a tritone, the most complicated ratio and the most complicated pitch. Now instruments don't actually play one pitch. They play many pitches called harmonics, and that causes each instrument to have a unique tone which musicians call its timbre. Now the harmonics add up to make a wave that's perceived as one pitch. The mathematical process to find these different mini-waves is called a Fourier transform. Let's say that wave 1 is the sum of two sine waves with frequencies 1.5 and 2, and that wave 2 has a frequency f. Analyzing how f affects the product of these frequencies, we can see that the product is greatest when the peaks of the waves match up, which means that wave 2 must have a frequency that matches wave 1. Looking from 0 to 3, we can see the average heights change, surging at two different frequencies. We can calculate the average height of the function by taking the integral from 0 to 3 seconds, then dividing by 3. That's the calculus method to finding the average height of a function. When we write the average height as a function f, we can see that there are two peaks, one at 1.5 and another at 2. But the blending of notes is not always that obvious. This graph appears to be a normal sine wave, but there are slight discrepancies. With the aforementioned process, we can see that there's only one peak, and that is at 2. But the process we used was actually a generalization of the real Fourier transform. For better accuracy, we can take the average of the function all the way to infinity and see the emergence of a second peak with a frequency of 2.5 but 1/10 as loud. So really, when you're listening to an orchestra, you're actually hearing multitudes of small little sine waves adding together to make a pleasant noise called music.